Good afternoon, everyone. Today in this session, we'll be discussing about the Kepler's laws of motion, right? There are three laws of Kepler, right? And all the three laws of Kepler's planetary motion will be discussed, right, in this lecture, right? So in the previous lecture, we discussed about the gravitational potential and potential energy, and we also discussed about the escape velocities, right? Now, in this lecture, we'll be discussing about the motion of planets around the sun, right? So Kepler put forward certain laws, right, which govern the motion of planets around the sun, right? And those laws we call as Kepler's law of planetary motion, right? So the first law of Kepler says that each planet moves in an elliptical orbit, right? The orbit in which planets revolve around the sun, right? Those orbits are actually elliptical in nature, right? With sun at one of the focus, right? So the first law says that each planet which are revolving around the sun are actually revolving in elliptical orbits, right? With sun at one of the foci, right? At one of the foci. So you know that there is a characteristic property of ellipse, right? That the distance of a point, the sum of the distance of a point on ellipse, right, from the two foci is always a constant, right? It's always a constant. You can see here, this is the point P where the planet is revolving around the sun, right, in elliptical orbit, right? S is at one of the foci, right? And S dash is another foci, or we can say it's another focus, right? Where S is the focus at which the sun is placed, right? Now this distance SP from the focus to the planet plus the distance of this planet from another focus S dash P, the sum of these distances is always a constant, right? It's always a constant. It's a constant, right? You can see here, if the sun moves in an elliptical orbit, right, there will be two distances, right? There will be two distances. One distance we call as perihelon, right? This is the point where the planet is very close to the sun, right? And this distance or this point we call it as perihelon, right? And this end we call as epihelon, right? So the point where the planet is very close to the sun, we call that point as perihelon, and the point where the planet is farthest, right? Farthest or at maximum distance from the sun. That point we call as epihelon, right? So these are the two important points, right? One is perihelon, another is epihelon, right? So planet move in elliptical orbit, right? With sun at one of the focus, right? That's the Kepler's first law of planetary motion, right? Now let's move on to the second law, right? The second law is what we call as law of areas, right? The law of areas actually says that the planet actually sweeps equal areas in equal interval of time, right? You can see here, there is a planet, right? There is a sun at the focus, right? This is the focus S, right? The sun is at the focus, right? The planet is moving around the sun in elliptical orbit, right? Then the area swept by this planet per second will be same for each and every interval, right? It will actually sweep same area in equal intervals of time, right? I can see, let's suppose this planet moves by an angle of d theta here, right? D theta, right? Now the area swept by this planet, right? By an angle of d theta will be this much of area, right? This much of triangular area, right? So this area we can write it as, this area will be equal to half of base into altitude, right? Half of base into altitude. So half base here will be base will be here the radius, right? R, and the altitude here will be, this is the, let's suppose this distance here is dl, right? And this dl distance will be the perpendicular distance. It will be nothing. It will be equal to r d theta, right? It will be r d theta. If this planet sweeps an angle of d theta, right? Then this area can be written as half r multiplied by this dl, right? Multiplied by length this dl, right? The total area swept by this planet when it moves by an angle of d theta, right? That will be half r square d theta, right? Half r square d theta. So this is the area swept, right? So area swept by the planet is nothing. It's half r square d theta. Now the second law actually says about the law of areas, that area swept per unit time interval is equal, right, for all the time intervals, or we can say it sweeps equal areas in equal intervals of time, right? So let's take the derivative on both sides. That's dA over dt, right, with respect to time, right? Now radius of this r here is a constant, right? R here is a constant. We can write it equal to half. So it will be half r square, right? Now you can see here there are two factors here, right? There are two factors here. One is r, right? The distance of the planet, right? Distance of the sun from the planet is varying continuously, right? And this distance is actually maximum at this point, right? That's the perihelion, and minimum at maximum at epsilon, right? This distance is actually maximum at epsilon, and this distance is minimum at perihelion, right? So dA by dt will be here equal to half r squared d theta over dt, right? That will be equal to half r square omega, right? And we know that v is nothing, that is equal to omega, right? Now let's suppose at any instant of time the planet is having the speed v, right, or the velocity v along this direction, and the angular velocity of this planet is omega, right? Angular velocity of this planet around this sun is omega, right? Let angular omega be the angular velocity of this planet, right? Omega is nothing, it's the angular velocity of planet, right? Now this dA over dt will be nothing. We can replace r omega with v, right? It will be half r multiplied by v, right? Half r multiplied by v, right? So the law of area says that d over dt will be half r multiplied by v, where v is the speed of planet or velocity of planet at any instant, right? Now you can see here it says that it sweeps equal areas in equal intervals of time, right? We can replace this. We know that angular momentum of this planet around this sun will be nothing. It will be the mass into velocity multiplied with the distance r, right? About the focus, right? About the focus, that will be mvr, right? So we can replace this vr here by L upon m, right? L upon m. So it will be L upon 2m, right? Now it means that if it sweeps equal areas in equal intervals of time, it means that aerial velocity is a constant, right? Aerial velocity is a constant. Is a constant. If aerial velocity is constant and this aerial velocity is nothing, it's angular momentum upon the 2m, right? The factor 2m. Now you can see if aerial velocity is constant, it means that angular momentum is also constant here, right? Angular momentum is also constant. It means that in case of planetary motion, right? Planetary motion, the angular momentum is a constant quantity, right? It's a constant, right? Total angular momentum is a constant, right? Now, if the total angular momentum is constant, right, or the aerial velocity is a constant, now you can see here, we can say that VR should also be a constant, right? If VR is a constant, it means that we can write V1 R1 must be equal to V2 R2, right? You can write this equation. V1 R1 must be equal to V2 R2, right? This is a very important equation, right? So V1 R1 must be equal to V2 R2, or we can say M1 MV1 R1 should be equal to MV2 R2 because angular momentum is a constant, right? Now it means what inference we can draw from this equation is that now let's suppose we have 2 points here. We have 2 points. The point one here is epsilon and the point two here is perignon, right? Now the distance, or we can say that V is inversely proportional to the distance here, right? V is inversely proportional to the distance here. It means that the point where the distance is farthest, right, farthest from the sun, the speed of the planet at the farthest point, or we can say at epsilon, will be minimum, right? And the same speed will be maximum at the distance where the distance between the sun and the planet is least. The speed there will be the maximum, right? So we can say at perihelion, the speed will be maximum, right? It will be moving with the maximum speed, right? And here at epsilon, it will be moving with the minimum speed, right? V minimum, right? So here at this point the speed will be minimum, and at perihelion the speed will be maximum, right? So V is inversely proportional to R. We can say aerial velocity is half RV, right? Or that's equal to L upon 2F. Or from here we can also conclude that the angular momentum is a constant in case of planetary motion, right? About the sun. Now let's use the same concept or the same law to solve this question, right? Now you can see a small satellite is in elliptical orbit, right? There is a small satellite which is in elliptical orbit, right, around Earth as shown. If L is the magnitude of its angular momentum, right? L is the magnitude of the angular momentum about the center of the Earth, and K is the kinetic energy, right? So there are 2 points here. There are 2 points here, right? The point one is that the planet is moving in a circular elliptical orbit, right? The planet is moving in elliptical orbit. There are 2 points, point number one and point number two, right? Or we can say this is the farthest point, or we can say it's a epsilon, right? And this is the perihelion, right? There are 2 points here. One we call as epsilon, another we call as perihelion, right? The farthest point is epsilon, and the we can say the nearest point is perihelion, right? Now you can see here we have to talk about the kinetic energies at point one and point two, right? Since the mass of the planet here is a constant, it's m here and m here also, right? Be it planet or satellite, right? Now you can see here from here that we know that at this point the distance is maximum, the speed will be minimum, right? The speed will be minimum here, and the speed will be maximum at this point, right? If the speed is maximum at this point, we can say that the kinetic energy at point two will be greater than the kinetic energy at point one, right? So this planet must be moving at greater kinetic energy at point two rather at point one, right? So the kinetic energy at point two will be greater than the kinetic energy at point one. Now talking about the angular momentum, we know that in planetary motion, angular momentum is a constant quantity. So it means that L1 must be equal to L2, right? So these are the two conclusions here. The kinetic energy at perihelion will be more than the kinetic energy at epsilon, right? Or we can say the angular momentum here will be a constant quantity, right? Now let's move on to the next question. A planet is revolving around the sun, right? In an elliptical orbit, its closest distance from the sun is r minimum. The farthest distance from the sun is r maximum. If the orbital angular velocity of the planet when it is nearest to the sun is omega, then the orbital angular velocity at the point when it is at the farthest distance from the sun, right? Now we know that we have to actually find the relation between the orbital angular velocities, right? We know the aerial velocity is a constant. It means that dA over dt is a constant here, right? It's a constant. And that constant is nothing. That's equal to half RV, right? Half RV. Or we can write this V as R omega, right? Can write this V as R omega, right? So it will be, by writing V as R omega, we'll be left with half R square omega, right? Half R square omega. I can see here, we have to find the ratio between the angular velocities at the nearest and the farthest point, right? So omega farthest and omega nearest. You can see here, omega here is inversely proportional to the square of the distance, right? Because area velocity is a constant, right? Or we can say omega final farthest upon omega nearest will be nothing. It will be nearest distance upon the farthest distance whole square, right? So this will be the ratio, right? This will be the ratio. So this will be the ratio, right? Between the farthest distance, right? Now the question is that if the orbital angular velocity of the planet when it is nearest to the sun is omega, right? Right. So the farthest point, the angular velocity will be omega times Rn upon Rf whole square, right? This is how we can find the angular velocity at the farthest point, right? Or the relation between the distance and the angular velocity is here, right? Now let's move on to the next question. A planet revolves around the sun in elliptical orbit. The aerial velocity of the planet is 4 into 10 to the power 16, right? Meter per second square, right? It should be the area. Okay, it's area velocity, right? The area velocity of the planet is 4 into 10 to the power 16 meters square per second, right? The least distance between planet and sun is 2 into 10 to the power 12 meter, right? Then the maximum speed of the planet in kilometer per second is, right? So we have to find the maximum speed, right? The least distance between planet and the sun is 2 into 10 to the power 12, right? Okay. Okay, we know that area velocity is a constant, right? Area velocity is a constant. That's t over dt is nothing. That's half times r multiplied by v, right? Half rv, right? So from here we can say that vr is a constant, right? Vr is a constant, or we can say that v1 r1 must be equal to v2 r2, right? V2 r2. So this is a constant here, right? V1 r1 is equal to v2 r2. Now the aerial speed is given as area velocity that's equal to. Okay, the area velocity, it will be twice the area velocity. It will be twice the area velocity, right? So area velocity is given here as 4 into 10 to the power 16, right? Meter square per second, right? Right. So V1 R1 will be 8 into 10 to the power 16, right? That will be V1 R1, right? That will be V1 R1. Now what we have to find out is that we have to find then maximum speed of the planet will be at the nearest point, right? At nearest point. The least distance between the planet and the sun is given. That's 2 into 10 to the power 12, right? 2 into 10 to the power 12. We have to find out the least, or we have to find the maximum speed, right? Or we can say V1 R1 has to be equal to 8 into 10 to the power 16. Now V1 we have to calculate, right? V1 from here, and R1 is given as 2 into 10 to the power 12, right? That's equal to 8 into 10 to the power 16, right? So even from here will be nothing. It will be 4 into 10 to the power 4, right? 4 into 10 to the power 4. This will be the value of V1, right? This is the value of the V1, right? Now, if this is the value of the V1, right? We have to find the speed at, we have to find the speed at which distance? Farthest distance, then maximum speed of the planet in kilometer per second is, right? So the speed will be maximum at the least distance, right? At the least distance, that comes out to be V1, that's equal to 4 into 10 to the power 4, right? Meter per second, right? Or we can write it as V1 is equal to 40 kilometer per second, right? The correct answer to this question is 40, right? So the speed will be 40 kilometers per second, right? Now let's move on to the third law of Kepler, right? Third law of Kepler. According to Kepler's third law, right? The Kepler's third law says that the square of the period of revolution of any planet around the sun is directly proportional to the cube of the semi-major axis of its elliptical orbit, right? Cube of the semi-major axis of its elliptical orbit, right? Now there are two axes, right? This axis we call as major axis, right? This is the major axis here, right? This is the major axis. And this axis of ellipse, we call it as minor axis, right? Minor axis. Now let's Uh, let's suppose the half of this semi-major axis is actually, or we can say the half of this major axis, we call it a semi-axis, semi-major axis, that's A from here to here, and it will be A from here to here, right? And let's call this B and B, right? So that's half of a major axis and half of uh, minor axis, right? Or we call it a semi-major axis or semi-minor axis, right? Time period actually, according to Kepler's third law, is that the square of the time period is directly proportional around the sun to the cube of the semi-major axis, right? It means that t square, if t is the time period, then t square is directly proportional to the cube of the semi-major axis. Now the semi-major axis here is a, so it will be a cube, right? That means t square is directly proportional to a cube, where a is the semi-major axis, right? So this is the Kepler's third law of motion, right? The time period, square of the time period is proportional to the cube of the semi-major axis, right? So it means that where the point, the ellipse, where the major axis is, semi-major axis is greater, and it means that the time period in that orbit will be more, right? Now let's apply the all the three laws or one by one to find out these to solve this problem, right? The mean radius of the Earth's orbit. The question says that the mean radius of the Earth's orbit around the Sun is 1.5 into 10 to the power 11 meter, right? The mean radius of the orbit of another planet around the Sun is 6 into 10 to the power 11 meter, right? The planet will rotate around the Sun in. So we have to find the time period, right? The thing we have to find here is nothing, that's the time period, right? Time period we have to find of another period, of another planet, right? Of another planet. I can see here. Now we know according to Kepler's third law that t square is proportional to a cube, right? T square is proportional to a cube, or we can say that t will be proportional to a to the power 3 by 2, right? A to the power 3 by 2. So from here, if we have to find the ratio between the time periods, that's t2 upon t1, that will be equal to a2 upon a1 whole power 3 by 2, right? Whole power 3 by 2. Now the question is that the A2, right? We have to find the T2, but the value of A2 here given is that's 6 into 10 to the power 11. The value of A1 here is 1.5 into 10 to the power 11, right? A whole raised power 3 by 2, right? So this and this will get cancelled. We'll be left with, it will be 4 here, right? It will be 4. It means T2 upon T1 will be equal to 4 to the power 3 by 2, or we can write it as 2 square into 3 over 2, right? That will be equal to 2 cube, right? That's 2 cube. That's equal to 8, right? It means that T2 must be equal to 8 times T1, right? 8 times T1. Now the time period of Earth around the Sun is 1 year, right? It's 1 year, right? Or we can write here T1 is nothing, that's equal to 1 year. It means that the time period of the second planet will be nothing, it will be 8 years. It means that the second planet will take 8 years to complete the one complete revolution around the sun, right? Now let's talk about the satellite motion, right? Let's talk about the satellite motion, right? We know that any object which revolves around the Earth, right? We call that around the Earth, right, in circular or elliptical orbit, right? With some fixed time period, we call that as a satellite, right? It's a satellite, right? Now you can see in this picture also, right? There is a satellite of mass m, right? It's moving around the Earth, right, in circular orbit, right, with some time period, right? Only because of the force due to gravity or gravitational force, right? So actually, the Earth provides the necessary centripetal acceleration or the necessary centripetal force for this satellite to be in this constant motion, right? To be in this circular motion, right? Or we can say the motion in the, to be in this orbit with some time period, right? So let's try to find out the orbital speed of this satellite, right? What is the speed of the orbit in the satellite? And let's also try to find out the time period of the satellite in this orbit, right? The speed of this orbit will be calculated. We know that the only force acting on this satellite is the gravitational force, right? That's towards the center of the Earth, right? That's towards the center of Earth, right? So it means that the Earth provides the necessary centripetal force for this planet to be in this orbit, right? So what we can do here is that the force due to Earth is GME multiplied the mass of satellite M upon the distance square. Let's suppose the distance between the satellite and mass is R, right? So we'll write here as R square, right? That's R square. That will be equal to centripetal force. That's mv square over R, right? Mv square over R, right? Now let's suppose it moves with the orbital velocity v naught. It moves with an orbital velocity v naught. If this planet moves with an orbital velocity of v naught, then we can find this orbital velocity, right? So orbital velocity will be nothing. It will be under root of gm upon r, right? It will be gm upon r, where r is the distance between center of Earth and planet, right? And satellite, not planet. So r is the distance between center of Earth and planet, right? So orbital velocity is nothing, that's under root of gm by r. So it will depend upon the mass of Earth and the distance, right? So this is the orbital velocity, right? Now talking about the time period of a planet, right? Talking about the time period of a planet, we know that this planet moves in a circular orbit, right? The circumference of the circular orbit will be nothing, it will be 2 pi r. The time period will be nothing, it will be circumference, that's 2 pi r upon the distance upon the speed, that's v, right? That's v naught, right? So it will be 2 pi r upon v naught. V naught is nothing, it's under root of gm by r, right? It's under root of gm by r. So the time period here is 2 pi r upon under root of gm by r, right? So we can write it 2 pi upon root of gm, right? Multiplied by r, multiplied by root r, right? So from here you can see here the time period is nothing, 2 pi r to the power 3 by 2 upon root of gm, right? Root of gm. Or we can say here, if we square it on both sides, it will be t square, that will be equal to 4 pi square, right? R to the power 3, right? Upon gm, right? So from here you can also see that the t square is nothing, it's directly proportional to the r cube, right? T square is directly proportional to the r cube, right? So this once again follows the Kepler's third law of motion, right? Kepler's third law of planetary motion, right? So t square will be proportional to the r cube, right? T square is proportional to the r cube. So this is the time period of satellite. This is the time period of the satellite, and the time period is proportional to the cube of the square of the time period is proportional to the cube of the distance of this satellite from the center of the Earth, right? So this is how we can find out the orbital velocity, right? So this is the orbital velocity here, right? This is the orbital velocity of satellite, and this is the time period, right? This is the time period of the satellite, right? And let's try to solve some of the question related to it, right? I can see here we have a question that satellites A and B are orbiting around the Earth in orbits of radius with ratio 1 ratio 4, right? Find the ratio of their orbital velocities, right? We know that orbital velocity is the thing. Orbital velocities are actually equal to under root of gm by r, right? For the satellites, under root of gm by r. And you can see orbital velocity is inversely proportional to the root of r, right? It's inversely proportional to the root of r. So v2 upon v1, we can write it equal to under root of r1 upon r2, right? R1 upon r2. So this will be the ratio of the orbital speeds of the two uh, planets, right? Or orbital speeds of the two satellites, right? Now it's given that the ratio R1 ratio R2 is given as 1 ratio 4, right? 1 ratio 4. It means that we can replace R1 by R2 by 1 upon 4, right? 1 upon 4. So V2 upon V1 will be 1 upon 2, right? It should be 1 upon 2. So the value of V2 from here will be nothing. It will be V1 upon 2, right? It will be V1 upon 2, right? Or we can say find the ratio of orbital speeds will be V2 upon V1. That will be 1 upon 2. Or if we have to find V1 ratio V2, it will be nothing. It will be 2 ratio 1, right? It will be 2 ratio 1. So that's the ratio. That's how we can find the ratio between the two planets, right? Orbital speeds of the two planets, right? So let's move on to this question, right? The time period of a satellite in a circular right? Find time period of another satellite in a circular orbit of radius 4. Time period does not depend upon the mass of satellite, right? In the previous section, we also discussed that time period or the orbital velocity does not depend upon the mass of a satellite, right? It only depends upon the mass of the Earth, right? Both the time period and the orbital speed here only depends upon the mass of Earth and and the distance between the center of the Earth and the satellite, right? So from here we concluded that T square is directly proportional to the R cube, right? T square is proportional to the R cube, right? The question is the time period of a satellite in a circular orbit of radius R naught is T naught. Find the time period of another satellite in a circular orbit of radius 4 R naught. So we can from here say that T2 upon T1 whole square will be nothing. It will be equal to R2 upon R1 whole cube, right? So this will be the relation between the two time periods, right? So from here, the T2 will be nothing. It will be equal to T1 times R2 upon R1 whole cube, right? 3 by 2, right? So this will be the new time period, right? Or the time period of another satellite, right? Now the time period of first satellite is T naught, and the distance between for the second satellite, the orbital radius is 4 times R naught. It will be 4 times R naught, right? Upon R naught, right? Raised to power 3 by 2, right? So from this and this will get cancelled. We'll be left with T naught times 2 to the power 2 into 3 upon 2, right? This 2 and 2 will get cancelled. It will be nothing. It will be 8 times T naught. So once again, you can see here, the answer is nothing. It's 8 times T naught, right? It means the orbital speed, right? Orbital speed of a, or we can say the orbital speed of or we can say the time period of the second satellite here is greater than this time period of the first satellite, right? Because it's proportional to the distance between the center of the Earth and the satellite, right? Get the distance, get will be the time period for the satellite, right? So from here you can also see if the distance is 4 times R naught, right? Then the time period becomes 8 times, right? The time period becomes 8 times, right? If the distance becomes 4 times, right? The time period becomes 8 times, right? So that's it with respect to the gravitation. We have discussed all the aspects of the gravitational chapter, right? We discussed about the gravitational law of gravitation. We discussed about the gravitational field intensity. Then we discussed about the gravitational potential and potential energy. And then we discussed about the different speeds, like we discussed about the escape velocity or escape speed, right? Also discussed about the orbital speeds, right? And then planetary motion and satellite motion, right? So this finishes the chapter gravitation, right? In the next lecture, we'll be starting with the system of particles and the rotational motion that will be started from the next lecture, right? So we'll stop here today, right? Meet in the next lecture. Till then, take care and goodbye.